So let's start with STL. So STL stands for Standard Template Library, and it was originally designed by Alexander Stepanov, and implementation and the spec goes public at 1994. So it's already 35 years old, and it still serves as a keystone of the standard library of the C++, and that proves that this library, the design of this library is remarkably good and well thought. And indeed, it was designed by a mathematician, and it's not the random thing, but it grounds the basic, very basic ideas. So it, as maybe you know, it consists of containers, algorithms, iterators, and functions. The important thing is that it has template in the name. So so everything in this libraries is just template, and to use it, you just instantiate the templates. And here's and here's the first complication. When you have some template that is that has class and parameters, you have to think about what this class is, what requirements what requirements are for this class to be this template instantiated correctly. And the set of requirements is called concepts in C++ world. That's why concepts are the key point of the STL design, and there are several of them, and each corresponds to the class of to some particular parameters. So the library itself, it's in a nutshell, you can you can describe it as follows. There's this key concept that is called iterator. Iterator is something that can iterate over the data and the reference to the value. Concepts, they own iterators and implement containers are they own iterators and implement them. Algorithms, they operate on iterators, and so in some sense iterators serves as a glue between containers and the algorithms that can be applied. And this basic structure creates the combinatorial number of usage possibilities. You can you can apply your algorithms to many of containers that you have, and you can extend the set of containers with your own container, or you can add the algorithm that is that can be applicable to already existing containers. And because it's the library is template, it consists of template. There are no runtime overhead. Well, it's important to know that library itself doesn't provide any any thread safety. So there are no logs and stuff like that in STL containers, but everything is thread compatible. So the design is such that you can easily do thread safe wrappers against STL containers and algorithms. Okay, let's start with iterator concept. Informally, iterators should behave something similar to the pointers within CRA. Let's look at this snippet. We have some CRA data, and we just iterate over it and output the result. Yes, we the pointer that in this case A, well, it can we can assign to this pointer. We can check equality, and we can increment, and we can dereference. We can substitute this data that is just CRA with std vector, and everything everything still looks similar. We have the only difference is that how we create the iterators now. Instead of copying from the data directly, we use begin and the end, and that's the idea. So the main algorithm, in this case the dumping to the std out, can be factored out and used both for the vectors and the CRAs as well. Okay, let's go into details and look at what is needed for the class to look like a CRA, look like a pointer within CRA. We can write down what we can discover. We can move forward, move backward, move anywhere, dereference, compare, and of course we should the class should be cheap to copy. Okay, all those requirements in the whole set of this requirements forms the concept that is called in the documentation random access iterator. We can notice that some algorithms don't need the whole set. For example, we don't need if we just dump in the data, we don't need to move in the random place. Yes, and we can, if we exclude this requirement, we will get bidirectional iterator concept. We can exclude more, and now this we only can move forward. Yes. Let's set yet another restriction. Suppose we can move forward, but only once. And we can dereference, but we can only use this dereference for reading the data, but not the writing. It's an input iterator. There is symmetrical iterator that is called out. Symmetrical concept that is called output iterator, where we can dereference only for the writing. The important thing that the syntax-wise, those requirements for forward input and output iterator, they are the same. And the only things that we add for the output iterator and input iterator specification, they can be only applied they can only describe as a comments, or they only can describe in words, so but not in the language syntax. And this is called semantic requirements. They're invisible for the that can be detected for the in the syntax, but we should just and we should we can only describe this concept in words, and this is an important thing. Concepts in the sense of the design, they are not the same as the concept in syntactic sense. In the C++20, we have concept as a syntactic feature. I will briefly touch it later, but it's important to understand that this is just an approximation for the real design concept. Okay, there's another concept that is important for the STL functors. It is something that that is callable. Now, after our talk, you know that callable can be function pointer, function, or some instance of the class that has a call operator overload. And the whole concept is called functor. And the additional requirement for the STL is that the factors should be cheap to copy. All functor parameters in STL, they are passed by value. And also it is assumed that the invocation doesn't change the state of the functor. Okay. Container is just STL treats containers as classes that have begin and end method that returns iterators. Begin iterators points to the start of our data and the end to the end of it respectively. But it also has size and empty methods and stuff like that. The possible alternative is to define the concept not within the methods of the class, but free functions that can take the container and return the desired thing. And in fact, this this approach was originally suggested by Alexander Stepanov, but it was rejected by the standard committee because in that time the object-oriented programming was the trend, and people think that having the requirement as a method is much more readable and clear. But now, but surprisingly, now the standard already have, in addition to that method notation, the standard has std begin and std size and std empty and end that that serve exactly that purpose. They provide the uniform access to the all containers that models standard container concept. Okay, there are two types of containers that STL models. The sequence containers that where you just they logically model the sequence of the data. There are several of them. They have different properties. Array is the most the fastest one and the most cheap, but it only can it has the fixed size that you can pass as a compile time parameter. Vector is the same as array, but it's dynamic. It can any numbers, any number of elements that you wanted. It's dynamic continuous array. Deque is a double-ended queue, so it consists of the it's not continuous. It continuous. It consists of the several chunks of the data. we have forward lists implemented a singly linked list and doubly linked list represented as std list. Yes, I have the slides for all of them apparently. So we can basically std array is just wraps the functionality that C array has, and does a little bit more. Firstly, std array can be returned from the functions, unlike C array. There is this language limitation inherited from C that you cannot pass C array from the function. And also, std array can be treated as a tuple-like object. So std get and tuple size and tuple element, they all can be applied to the std array, and also structured bindings can be applied as well. So vector. Its implementation is trivial. So you have the data allocated in the heap and the size of it. So the vector the vector is a class that owns two things: the pointer to the data and the size. And interestingly, okay, there's this small snippet where you have an empty vector of integers, and then you are pushing back the elements to that vector. So how many times each element is moved on average? And maybe it's counterintuitive, but the answer is the answer is 2. It's not proportional to the n, but it's a constant thing because of the strategy how vector allocates the memory. If you need to make your push back detects that you need to allocate more memory, then the vector is allocate twice memory as it has had before, and so it allocates in advance. That saves memory allocation and copying that can be quite expensive. Okay, under the hood, and it is documented in the standard that vector is implemented exactly that way that I have described, and it always has continuous memory, and basically the iterator that vector provides is just a pointer to the data, and we can use vector if we're wrapping some raw C interfaces. For example, if we have some C interfaces like that looks like that, we just pass the pointer and the size. We can easily wrap it to the vector such in such way, and this will work. Okay, but there is only one exception, unfortunate exception, std vector of Boolean. And unlike any other instantiations of the vector, this vector is not contiguous. And the reason is purely historical, and someone wants to demonstrate C++ specialization, class specialization in application to the std vector. So in fact, std vector, so the memory allocation is kind of compressed. And in practice, this means that you shouldn't use std vector of booleans in your code. Try to avoid that because it's not continuous and it is not even thread compatible.
The next is deque. Deque is organized as deque is organized in chunks. So the memory is allocated in fixed chunks, and we have this chunk table that contains the pointers to the concrete chunks. And the advantages is that push front and push back are very effective because they are constant time. If it needed an extra chunk is allocated in memory, and it's constant time against the size of the whole deque. And also it has random access iterator, of course, but that the disadvantage that it has have to have two references. So the list is and the single linked list is obviously implemented as a list structure. So it has internally the elements of the container are placed in the boxes where each box knows what is the next and the previous element, basically. And the advantages is that the insertions are constant time. You just and they have even the special name splice. There's no random access, and also the advantages is that that iterators are always valid. Even though you modify the container, the iterators of the list, they are valid. In some algorithms like sort, they are implemented directly in the list container, and to do the sort of the list, you should not use std sort. It will not work because there is no random access. Okay. For the practical programmer, each time you need to you store your data, there is the practical question what to choose. STD vector should be used as a default. It's fast and it consumes less memory than others. If you are implementing something like queue, then deque will be even better. Just check your usage pattern. If you have a lot of pop and push front or back, this is the case for the deque. And for the list, the recommendation is it only makes sense to use it where the performance is not the issue, but you want to have references and iterators always valid. Okay. Also, STL offers associative containers. Basically, there are two. There are three kinds of them. Set is just the ordered the container where the elements where the elements are placed placed in order. There is a map where you have key value pairs and you can access your value by key. And multiset is the same as the set, but it is allowed to have several identical elements in that, and multi-map is the same. For the multi-map, you can have several elements with the same key. And there is the unordered versions of that. That is the plain versions are implemented as a binary tree. Unordered are implemented as hash tables. And of course, you can specify the comparison function. For by default it is std less, so we compare so the first element will be the smallest one, but you can set your own, and for the unordered variations you can customize your hash function and the equality functor. Okay, there are some requirements that are important that compare a functor that is passed to the associative containers should be same. It's if and it should be quite straightforward. Sometimes people try to do something complicated in the comparison functor, and the result is the existence of very subtle bugs that hard to find. And the next not obvious requirement is that associations of the set should be virtually immutable. This means that you cannot place something in the set and then change the values such that that it ruins the order. Okay, let's but so even though the usage of the STL library is more or less intuitive, there are some nuances. For example, there is associative containers. They have several ways to insert the new values. You can use insert function, and you can insert with the bracket separator, and the semantics is slightly different. And also you can access with the bracket operator, or you can access with the add function. So, and you should understand what the difference is. Where you, for example, in this case, where you try to insert element A in the map that already has element with the key A in the map that already has that key. What happens? Insert insert it will not change the map at all, because and if you but if you insert like that, the map will be changed. Yes, and the result will be for this short snippet will be the following. If we want to access the element that is not in the list, we will have compile time error, or runtime error in this case. Okay, let's go to the algorithms. There are, I think this is the most, the biggest file in the standard library that contains all algorithms, and the number of the algorithms is huge. I don't want to cover all of them. They are very well documented, and and basically you can do a lot of things with the containers. Something that can be confusing for the not experienced users. There is this std remove algorithm. So let's have let's assume we have a vector. By the way, this is the example of the class template deduction feature of the C++17. This in this snippet we don't specify what type what the type that is used to instantiate this vector instance, and this type deduced from the from the data, because literals are integers, so it will be vector of integers. So we want to remove the second algorithm, and we the all tools from this vector, and we expect that we will end up with a vector without 2. But basically this will fail, because remove actually doesn't remove anything. What it does, it returns, it moves the elements to be removed at the end of the of the range, and to do the actual removal of the data, you should call vector arise method that and pass what std remove returns to you as a first parameter, and the end of the container as the end parameter. In this case, it will work as desired. Okay, some little there is this small STL algorithm that is called swap, and it just swaps the elements. It takes 2 references and it swaps the values in those references. And there is the default version of that uses temporary, and they move into from the temporary to the reference. But it is intended, it is expected that someone can specialize the swap, and usually the way people should do it is to define their own swap that is specialized by this value. And in this case, by the way, this friend definition is you can so initially friend keyword was used to declare something as that declare the functions that can use private members of the class. But this structure obviously doesn't have private members, it's a struct, and the friend has the friend in here has the different meaning. This means that swap function will be searchable by argument dependent lookup. Mauro had mentioned this algorithm yesterday, and but only in this context. In other contexts, swap will not be visible. So we and if we naively will try to use std swap, it will not redirect to this swap. And to do and this snippet will fail. What we should do instead, we should add using std swap in our snippet and use unqualified swap. In this case, std ideal dependent lookup will work, and the desired version of the swap will be called. So, and this based on the fact, this trick based on the fact that that ideal dependent lookup works only if you with unqualified functions. So also STL contains some useful adapters that like queue, stack, and priority queue. That queue implements FIFO, stack philo, and priority queue is a nice wrapper against heap merge algorithm. So I would skip the details. Well, as you know, C++ have been changed dramatically since the STL library was first implemented, and it turns out that that most of the changes in the language were driven by the STL design and the current implementation of the STL uses each and so almost every new feature that we have in the language. For example, as for initializer list, it's all containers can be all containers support it. You can do you can use that, and you can benefit from the automatic conversion from the initializer list, like in this case. We can also use assign operator from initializer list, and this this is equivalent of clearing all the content of the container, and it's quite handy in many cases. And we can use ranged-based for loop. I don't know if you know, there is this new form of the loop where you provide the container and the element that will be used to enumerate the container. So, and this this feature range-based for loop is designed specially for the STL, and it's especially useful here. Initializer list uses can be nested, and it's also can be utilized in STL containers, and also it's the convenient thing is if you have your function defined that takes vector, for example, you can pass initializer list, and well, it works. Also, move semantics fully supports by STL. the requirement for the elements since C++11 they're softened from copyable to movable, and this allows us to use unique pointer as an element of our containers. So and basically because unique pointer, I don't know if it was covered or not. This is the STD unique pointer, it's not movable, so because it assumes that your data is kind of unique, and if you try to do for example STD vector of unique pointers, STD unique pointer is movable but not copyable. But if you try to do STD vector of unique pointers, it will also inherit this feature. It will be movable but not copyable. And since move semantics works for all STL containers, there is no reason to store the raw pointers in containers anymore. So if you have them in your application, probably you are doing something wrong, and it's much safer to do it with smart pointers. Okay, so as I said, range-based loop syntax works, and for all containers, and this makes for each and transform algorithms as they are in the STL much more or less useless, because you can express the same thing with the same performance with range-based loop much clearly. Also, perfect forwarding perfect forwarding is reflected in the STL changes. You pushback supports that, and additional you have this emplace back method that explicitly doing differs the associations of the so there's also a new method in place back and in place front for some containers that that takes parameters and creates the elements in place with these parameters passing to container. So it's only possible in the language where this perfect forwarding and universal after perfect forwarding and universal universal references were invented.